So please join me in welcoming Professor Tan to our conference today.
Thank you. It's actually my first time to Penn State. Thank you for having me. So I'm going to tell you about the work done in my group on hybrid quantum photonic circuits and the quantum frequency conversion. So before I start, I want to tell you about my research interest. So at Yale, we build integrated photonic chips to manipulate photon on chip and that enhance the light matter interaction. So when we talk about light matter, it's more like a generalized matter. So those include light interaction with mechanical resonators and interaction of light with spins and interaction photon interaction mediated by nonlinear optical material. So today I'm going to focus on this topic of integrated quantum and nonlinear photonics, with special emphasis on integrated quantum frequency conversion. So, so the major motivation for building photonic quantum chip is for its scaling advantage. These is a boson sampling machine was built by Jianwei Pen's group at the University of Science and Technology of China. What you see over here that involve 20 optical input mode and about 40 to 60 optical output mode. Those are like optical beam splitters that split the light to do the optical logic. And those are array of detector head. So you can see that even though the market is as a tabletop quantum computing system, pretty expensive, also very large. So if we can integrate other detectors in the photonic logic and the photonic light source on the same chip, there is a significant advantage for chip scale quantum computing. And another motivation is quantum networking. So a lot of us envision in the future quantum network will be consisting of like an interconnected quantum processor load. So to build this kind of a network, we need quantum transaction device to distribute the entanglement across the different computing nodes. So this quantum interface is very hard to make. For example, one of the mainstream quantum computing platform is a superconducting qubits, which operate on microwave photons in the mini-Kelvin dilution refrigerator. And those microwave photons cannot come out of room temperature and maintain quantum coherence. So these are very simple prototype of two-core network device that was built by ETH Zurich group about 3 years ago. So these actually physically connect the two dilution refrigerator together with a vacuum cryogenic tube. So many of us in the field believe we can do better by using optical fiber to connect different quantum computing nodes. Here, we need a very efficient quantum frequency transducer to convert a microwave photon to room temperature and deliver to the remote quantum system. You need a very efficient converter that you can achieve with integrated chip because you have enhanced light matter interactions. So those are motivation. As far as the implementation, silicon photonics is the most advanced photonic platform. Today, silicon photonics are very commercialized. They're used in a lot of data centers. The problem is silicon photonics is not a good platform for quantum optics or nonlinear optics. The reason is silicon has like a center symmetric crystal. It does not have the Chi2 nonlinearity we would like to operate quantum optic devices. So some of the very basic functions, for example, like second harmonic generation, spontaneous optical frequency down conversion, optical parametric oscillator, those very simple quantum optics techniques you cannot realize with devices. So in our group, our goal is really to integrate those nonlinear material, like with Chi2 nonlinearity, which is the nonlinear material, to put on the integrated chip. So the hybrid integration, including the material with bulk inversion asymmetric material on a chip to harvest this Chi2 nonlinearity. To manipulate the photon and to realize microwave circuits, we also need to integrate like superconductors on a chip. So all my work involved integrate some of those materials on the silicon photonic platform. So, so in that sense, in the context of manipulating the photons on a chip, we need to have a very efficient detection of photon and a very efficient photon light source, so the generally entangled photon pairs. And we also needed to convert the photon from one color to other color without destroying its quantum covariance. So that's what basically I'm going to tell you a story about how we can achieve this goal with integrated photonic chips. So let me start to talk about the photon detection. So in order to manipulate the photon, we need to develop a very reliable tool to detect photons. So what do you see over here is a huge array. Those are single photon nanowire detectors. And those detectors, it's a very simple device. It's basically a very thin superconductor. You need like a meander. You attach it to an optical fiber. And you can count a single photon with very high fidelity. So the basic analysis of this detector is very simple to understand. So when photon land on those wire, it destroys the local superconductivity. And with the current bias close to the critical current, and you basically you form a local hotspot, and that hotspot grow and cut off the supercurrent. And you can register that on at a very fast speed with very high efficiency. And that creates single photon detector. But those detectors are very hard to integrate because of normal incident with your camera. So, so what we did back almost 10 years ago, we developed a technique to pattern those superconductor nanowire on top of a waveguide, a silicon waveguide or silicon nitride waveguide. And by allowing the light to very strongly couple to those superconducting nanowire, we can build a very efficient detectors. And very fast too, because the wire is very short and very low inductance. What's most important of this detector is that they can build the photonic integrated circuits. You can build 100 of them, 1,000 of them, string them. So you can build a very efficient single photon detectors. So those are very really mainstream detector technology being utilized today in this quantum photonic optical quantum photonic computer chips. There's one caveat. In quantum optics, we need to resolve so-called photon numbers. So, the light coming in, it's not just 1, 0, 1, 0. It's actually have information about how many photons there. So this photon number resolving detection is really the ideal detector that allow you to detect. And these detectors can only detect the presence or absence of photons, but cannot resolve the photon number. So for decades, people wish to could have photon number resolving detector. You can probably you heard about the Schrödinger cat, right? Those cats stay the basically based on the photon number. So you should be able to resolve that. So the question is, how do you resolve the photon numbers? Instead of saying 1, 0, 1, 1, you want to still read it 1, 0, 3, 2. And to see that kind of information is ultimately the goal of the quantum optics community. So for those of you familiar with the photon detection, you probably know this device called transition edge detector. So these are basically a barometer made of superconductor, very thermally isolated, and that can count the photon, about up to 10 photons, resolve up to 10 photons. Does not have high speed because the barometer, low temperature millikelvin, the barometer very slow, so only 10 microsecond response speed. So we spent a lot of effort try to build a different detector, a different realization. So this is what we come up, a photon number resolving detector that can resolve up to 100 photons. So what you see over here is optical waveguide here in the center made of silicon nitride. So light come in, will propagate along this waveguide. On this waveguide, you nanowires here. Those are similar wires, superconducting nanowires, and we put it in series, interconnected through a slow microwave line, transmission line. So when light come in, each of these sections is designed to absorb 1% of light. So if you have light come in, and if light, one of the photon land on those detector, it actually send 2 pulses through this transmission line. These 2 pulses are propagating in the opposite direction. So when you look like by the end over here, look at the time of flight difference between these 2 pulses, you know which detector fired. Then you count how many detector fire, you would be able to tell and what is the photon number in that package of photon. Okay, so there is a lot of it. This device is very complex to fabricate, and one key requirement is that the microwave propagation speed should be 100 times slower than optical propagation speed. So our oscilloscope can capture those pulses. And we designed to have a microwave propagation along this long transmission line, it's more than 10 meters long of transmission line, really packaged in a small footprint. And only 100 nanoseconds. And that means 100 nanoseconds, this is 10 microseconds, this is already 100 times faster than transition edge detector. And that's meet the requirement in most of quantum computing applications. So these devices work extremely well. And here I show you what we see from a typical oscilloscope when I send a thermal light in here. So they see thermal light has average photon about 6 photons per mode, per pulse. And you can see each of these pulses, you can see for the first pulse, you see about 16 photons over here. Okay. And the second pulse, you see only 2 photons. And you can repeat that measurement many times and you build up your statistics. Here, your histogram, here you make an average, you can see that these photon number distribution in that optical mode very nicely match Bose-Einstein distribution. Okay, that's just a signature of thermal light. However, if you now turn to coherent light, which is basically attenuated laser, if you set that at the same average photon number about 6, you see the fluctuation of photon number is much reduced. Okay, there is still fluctuation, so that's just coherent light fluctuating. Right? There is one limit, and you look at the statistic, you see photon distribution, which matches extremely well. That's what is the coherent state of light, photon distribution. So you can also increase the number of photons in your mode. You add to, say, for example, average of 54 photons, and it becomes less fluctuating, and distribution of photon number very closely match the boson Poisson distribution. The reason is not a perfect matching here, at the tail here, is because I only have 100 elements in this detector. If I increase about 1,000 elements, which we could do, and we would become able to detect more than 100 photons. So this is a really nice device. We did spend like 6 years to make it work, but we're very excited about this device. And there are a lot of things you can do just with this device to study the photon at a very fundamental level, study light at a very fundamental level. For example, you can measure the optical like photon correlation at a very high order. Some of you probably do photon correlation measurement. You normally do G2 measurement, 2 photon correlation. You can do 3 photon correlation. Our device can do 15 photon correlation. That's never been done. Okay. And you can also look at quantum limited discrimination of a coherent and a thermal light. Well, the sunlight comes to us as a thermal light, right? And if you shine laser from the moon to us, that's coherent light. How do you tell the difference of light? And there is a fundamental limit that we show that with our detector, we can discriminate that very thin light at a quantum limit. And also you can subtract a photon from a coherent state or from a thermal state. So there are really, really a lot of things you can do. I just tell you an example how to do the photon subtraction, okay? So here, this is diagram. We have 100 element photon detector over here. And we separate those 100 elements in the 2 groups. The first group can be, the 2 groups can be treated as 2 separate photon number resolving detector. And the first detector basically condition on the subtraction process. So you detect 1 from this detector, you know you subtract 1 photon from this light source. And the remaining photon can be subtracted, a photon hole in your bowl. And you can subtract 2, you can subtract 3, you can subtract whatever number you want. If you just look at the first detector, how many flash. And now we're interested in subtract the state. So if you subtract 0 photon, you have an expected Bose-Einstein distribution, okay? But if you subtract 2, you see it becomes a more Poisson distribution, okay? If subtract 4, becomes a more Poisson distribution. So then when you more substitute the thermal light, it's thermal light and it subtract photon, it becomes more like a coherent, okay? And very interesting, when you subtract the photon from a thermal light, the average photon number increase. It's a very counterintuitive, but what happened is really thermal light is a very bunch, right? They're bunch the photon. You subtract, you destroy the bunch means you can add it on. Or the more coherent, the average photon number increase. Okay, so these are really power. Think of an integrated photonic, what it can do. You can detect photon really effectively, and this you can really get a quantum limited detection of the light. All right, I'm just going to pause over here and query if there is any question about photon detection before I move on. Like 1 photon. You just look at it. It is. Is it just? Is it? What's really nice that after being for that, you have a 2 photon number resolving detector. So you can that allow you to subtract a 0, 1, 2, 3. If you just have a regular detector, you'll not be able to do that. Right. You can do that. Yep. Yep. Right.
Another question I have is maybe in nighttime, how cold does it have to be?
Those actually work out just 2 Kelvin. It's very easy, right?
Yeah, but
Most of my questions go far below 2 Kelvin. Right, most of our questions go mini Kelvin. Yeah. Coherence of the laser source. But that
have outline field.
Yeah. I just do the detecting job. I don't control the source. In this case, that's the next section.
Question like this, like which detector actually clicks, is it actually random or it's kind of like depending on the time of arrival?
There's no information about the time arrival of a photon itself. It's hardly that. Remember, your coherence of your light source is way longer than my device. So this beam splitter is really splitting in a random direction. Don't think this one first, this one second. Yeah.
So there are certain chance that the photon just goes through and will get detected.
And no, is there one person, and then it goes through is less than 1%. So that's very small. We designed to have a school of those. You see, that's why at the later part you get bigger. Why are you becoming bigger?
So you could actually get a reflector on the other end and it gets double efficient.
It's the equivalent of that. We design, if I have 1,000, and this right now is already 1%. 1%, you don't have much going down there. The efficiency is 100% anyway, so we can get, that's not, efficiency is not really a problem. Yeah, it's really to assess the photon number in that mode, which is hard.
Is there a way, this you work with the optical waveguide? Is there a way to do it without the optical waveguide?
You could, yep. You just get a 1 to 100 beam splitter for the 100 detector. You can do that. That's going to be the challenge. Yeah, that's what I showed at the beginning. And each one they charge $16,000.
How much is this? What did it cost?
It costs about $1 million per piece. Because my graduate students spend 6 years on it. I have a mini copy of this.
How big is that?
Huh?
How big?
This whole chip, this device. Do I have a scale point here? 400 micron here.
That's really big.
And that's the hard part about it because we use a university clean room. And this a big chip is a really challenge. My students figured a way how to get rid of the dirt in the university clean room with like a 7-layer E-beam lithography. Really hard. And that's actually, but if I get a global foundry to do it, they could yield it very much higher. They don't have a problem. And these wires so long, this is a challenge. Okay, so let's talk about the photon detection generation. And so, there's a lot of ways to generate photons. Quantum dot, universal quantum dot, and many different ways to do it. And you can use the color centers. What do? We use a canonical way to generate photon, nonlinear optics, parametric down conversion, parametric oscillators. Okay, so for that, we need a nonlinear material on the chip. And so here I show all the nonlinear photonic material people use in the photonic community. And so those triangles, those material with the central symmetrical crystals, most like CMOS like material, the silicon, amorphous silicon, crystal silicon, carbide, silicon carbide, silicon nitride, hydrogen glass, diamond, silicon. And those are Chi3 material. So here the horizontal axis is the band gap, and these are the Chi3 nonlinearity or current nonlinearity. You see this is inverse dependence. So smaller band gap, larger nonlinearity, which is expected, right? And we are interested in the Chi2 material, quadratic material. Here are those circles, and those are 3-5 semiconductors. Gallium arsenide, gallium phosphide, gallium nitride, gallium nitride, and those bulk inversion symmetry broken, right? And there's a special material, lithium niobate. Band gap is here, and the color code tell you the optical nonlinearity Chi2, which is on the right side. Again, smaller band gap, larger optical nonlinearity. But in quantum optics, we actually want not only want large nonlinearity, we also want large band gap. The reason with larger band gap, you can process the photon on visible color. That's very important for nonlinear optics and to generate photon pair. You do not really want to work narrow band semiconductor. And that's not surprised that nitride is the material we have identified as the best material in our lab to build nonlinear optics and nonlinear photonic devices. Of course, you can work with gallium nitride or lithium niobate as well for all the devices I'm going to show you. And we have versions that work with lithium niobate. Okay, so in terms of aluminum nitride, we really like aluminum nitride because of large band gap and very nice near nonlinear optical properties and very widely used in MEMS system. And also for solid state lighting and blue lasers, the high power transistors, all this really make 3 nitride, aluminum nitride material very scalable, but not only can grow those material at a large quantity, and you can also process the material in kind of a standard foundry process. So in our lab, we use 2 different types of aluminum nitride material. The first type is really follow the MEMS process to deposit aluminum nitride on oxide. You can form a waveguide. The thermodynamic works so well that when you deposit aluminum nitride, even at a low temperature, it crystallizes and they form like a domain, C-axis aligned domain that give you optical nonlinearity. And this domain is very small, only 20 nanometer. It does not introduce much scattering at visible light frequencies. And then more recently, now we use a single crystal material. You can see in the middle of the domain, you actually become very narrow, and the surface become more smoother. Here's a 2 nanometer roughness, and here is like 0.3 nanometer roughness. So as a result, we have a much higher quantity factor with a single crystalline material. Those are MOCVD aluminum nitride. And the typical quantity factor with this, like a polycrystalline material, get a Q about around 1 million at the telecom wavelengths. But for the single crystalline material, we got a 5 million. And now we try to push to 10 million with a kind of a quantity factor. And you also can operate this device down to UV band. Right now it's 390, you have a 1/4 million cube. The quantity factor really tell you how much loss in your materials. Okay, so that was a very low loss. That means you can trap a photon in a resonator for a long time. And then that way you can enhance your optical nonlinearity. And you can do a lot of interesting things about nonlinear optics with those resonators. So once you trap the photon right here, you want to perform nonlinear functions. The very important nonlinear device requirement is the phase matching. So if you work on nonlinear material like a lithium niobate, you know you achieve the phase matching through the theoretical polling, and you allow you to gain extra momentum from the polling. For this device, we do the phase matching by using geometric phase matching. So when you do it, you vary the width of those resonator waveguide. And as you vary the width, you can identify 2 modes. One is at the fundamental frequency, for example, 1550 nanometer, which is telecom wavelength we all use. And then the other are the second harmonic around 775 nanometer, which is a higher order mode. And they have the same index. At that width of the waveguide, you got a phase matching. Without phase matching, then you can enhance the component between the 2 color lines and get a very efficient photon color conversion. I'll just give you an example over here. These devices, the 4-port device, you send the telecom light into this port. And if you are phase matched, for example, this device, you see that the telecom light can up convert second harmonic generation to 775 nanometer. Under your microscope, you can see with your bare eye, you can see the red light come out. Okay. And with that, we can really enhance our second harmonic generation efficiency from about 10 years ago to 24% per watt right now, from 17,000% per watt. And those numbers really is a measurement of nonlinearity you can achieve with these aluminum nitride, which is relatively weak nonlinear material. With a lithium niobate, you can get to 5 million percent per watt. There's also other record we achieve. Even here is already a record. Now you just can get better and better. So you can see that we're very really obsessed with this nonlinearity, and the reason is the following. So here I'm plotting the fundamental light power, which are the 1550 nanometer, and this harmonic power, which are the 775 nanometer. And you can see this is plotting a log plot at a low power regime, no pump power, you see the quadratic dependence. Well, I have a quadratic material, you have a quadratic technical harmonic dependent on fundamental mode, right? However, at a certain threshold beyond 3 milliwatts of technical light, you see the start deviate from a quadratic behavior, become more like a linear. So what happened? Your fundamental light converted to the second harmonic, the action started to convert back. So because the two lights become strongly coupled within the resonance. That actually strong coupling, and that strong coupling allows so-called mode splitting. So if you are phase match, you see this mode splitting. But if you're not phase match, you don't see that mode splitting. Okay, so the phase match requirement that two color lights propagate in the same direction. If you propagate counterclockwise, you're not a phase match. So that actually gives you an isolator function, right? That's a lot of people talk about isolation, symmetry, all this. This is simple. This is like a really phase matching coming from here. So these actually measure this mode splitting, measure your coupling strength between the two color of light, which is very far away, 200 meters away, and they couple together through this nonlinear material. And you can do a lot of things with this, and many applications of this. Of course, some people call this optical induced transparency. You can look at long-range spectral devices. You can make a narrow line laser at a new wavelengths. You can make a very low threshold parametric oscillator. You can create a squeeze light. You can build a high rate photon pairs, which is really the motivation we started this project. And let me just give you an example of some applications. One of the major applications, we want to use this nonlinear device to address some atomic state. Rubidium, 85, 87, the transition frequency, we build an atomic clock. Normally 780 nanometers, for example, 780.12 nanometer, and 782.45 nanometer. Because I really need the last digit here, right? If you want to work on this, you need to always on there. So the challenge here is you want that precision that's given by nature. You have a mechanical, you have to make this device to match that wavelength. That's hard. So what do? We make an array of 16 resonators. Each resonator only varies by 10 nanometers. So that allows us to cover phase matching window the whole C-band. Okay, so that's our strategy. In this example, I have 8 resonators. So you can see every 8 resonator, and you see 8 resonances. So if you have a 16, you bridge this gap. So we can cover all the wavelengths, and you send the telecom wavelengths light in, which is cheap, easy, and you can generate 780 nanometer light, narrow line width, and can address the atomic transitions. And those techniques right now are also being applied to the trapped ions, trapped atoms, to generate the to control and to interrogate those very narrow transitions in the atomic system. Well, so this is the second harmonic that I was showing you earlier. You can reverse that because you have a strong coupling line between the two different colors. You can build like an optical parametric oscillator function. And if you're in the optical lab, you have audio, right? You need a huge amount of power. But with the on-chip, you only need a milliwatt to produce a laser. And here's an example. We actually send the pump at 775 nanometer, and we produce a laser at 1550. And this is degenerate, and this is non-degenerate. You can see I can make a laser, cover almost 130 nanometer wavelength, the whole C-band with one color black. Okay, so it's a tunable laser, but you don't really have a laser there. You don't need a gain media at 1550 nanometer. So those are OPO. And if you reduce your OPO just before the optical parametric oscillation, you have optical parametric amplifier, or you have a squeeze light. And you can build optical parametric amplifier that way. You can also build a squeeze line source that way. But the squeeze line is really, really hard to measure. And so what we do, we actually go further below that threshold to measure the photon pairs. And that's actually the next experiment. You can see that we drive that resonate at 775 to measure 1550 nanometer light as a pair. So you measure the G2 I mentioned before, and you can see that the photons are bunched because they generate by pairs, they all bunch. But if you detect one photon, look at the other photon, you see that that photon becomes single photon source. That is anti-bunch. And we found this in aluminum nitride, there's really very little noise because the RAMA is weak and the signal, the device, everything is pure. There's just two model and right there. So you have a very high speed, and the photon light source generated this way is almost quantum limit. Okay, so this basically address the question: how do you generate the entangled photon pair on a chip? Use this nonlinear resonator with center bulk inversion safety broken material. In this case, when I try to generate this device, you can also use lithium niobate. We always find that aluminum nitride can take much more power than lithium niobate. That's the advantage. Okay, so is there any question of light source answer? Yes.
For like the negative compound or the component of the for the so-called division, so that the coupling factor conversion. Like the top guy coupling with the ring resonator was harder than the bottom guy. Yeah.
Oh, that's just a different wavelength because the reason you see the waveguide coupling the resonator, you see fluorescence wave, right?
Yeah.
Because the shorter wavelengths have a better wave coupling, you need to make them closer. And you also want to make it strongly coupled, so you want to make an interaction longer. It's just different wavelengths. See, that's a design factor. That's what we call wrap around. And the same for the 1550, the wavelength is much longer. So you have a much bigger fluorescence coupling. You can use the face much here. But for this, you just need to engineer the device with different wavelengths. Short wave, and I work with a 350 nanometer like that. Tiny. It's very small. It's very hard to make. Any other question? Yep. No, this is a fully phase match. Quasi-phase matching, I cannot. I think here the Penn State there is a recent result that you can reverse the system super and reverse the unlike domain, and that'll be really nice. You cannot do that. Single phase one. Air is too loud. Here's electric chip, not a parallel. You cannot do that. It's the same. It doesn't. It's that's.
But you have both single mode where overlapping.
That's beautiful. Yeah, that's why we have a separate paper on that. You sacrifice the mode integral in this geometric phase matching. Exactly right. Yeah. So you can do direct TE to TM mode matching. And right now our efficiency is way more than I need. And actually I need to worry about the thermal problem. That's a bigger problem too. Right. That's the problem with lithium niobate. You generate a light out of UV light and they produce like a photoreflect effect. You have to work on solve that problem.
Doesn't measure like the SPTC generation, right?
It is a
Yeah, but this measure like the rate you can get and compare like with the similar kind of like lens structure or video.
Lithium is more efficient. This is like for this device, I have a phone number. The pair generation rate is like a 3 meg pair per milliwatt. For our most recent, we have a 3 gig pair per milliwatt. So the rate is pretty high. That's rate isn't that a problem anymore because this device is a very strong. And BBO, the free space is one pass.
One more question. A lot of people in the department who are working with like applications at the surface where you are supposed to not have this problem of phase matching because they're going to do nothing. What do you think about that?
What do I think? You need this. You need this. You need this queue. Okay. You need the queue of 5 million. Give me a 5 million, we can do a lot of things. But if you queue of 1 or 10, that's really there's most of a photon pair generated get lost before it come out.
I'm not talking about metallic, I'm talking about the electric. I think not 1 million, but few of the thousand.
It's hard.
Yeah.
Right. Right. You need this high Q. That's really the enabling. If we can get rid of loss, that's the gold standard. Any other question? All right, so let me go down a photon color conversion. I already show you some conversion like second harmonic generation, parametric down conversion, but they're a little bit different. So when we talk about a frequency conversion, quantum state transfer, we're talking about you transfer quantum state between different cubic systems, distributed quantum entanglement between the cubic systems. So those are the summary of some of the cubic systems studied in the community. Property ion, property superconducting junction qubits, property of contenders, and there are other systems like photon atoms. They're all different, right? So if we can build a quantum interface between those different cubic systems, we can combine their advantages. And that's the idea behind it. You see a lot of community, a lot of people working on those quantum frequency converters really try to build a quantum interface between different cubic, heterogeneous cubic systems. So what is the quantum frequency conversion? How is that different from your active optical? So if we think of quantum information, just like classical information, it's encoded on the carrier, right? So for microwave qubit, include 10 gigahertz or 7 gigahertz carrier. For optical qubits, it's probably on the 200 hertz or top of the ion, probably 400, 600 hertz. It's just a sideband on the carrier. So optical frequency, quantum frequency conversion, one very important goal is to really, we want to translate a photon from this color to that color, but without losing the quantum information, without changes the photon statistics. Okay? So you can also think about the sideband being copied to the new carrier. Okay? Or in terms of IQ space, so really the regular function does not change. So these are actually a very strong requirement. What's the requirement? You require the gain to be 1. You want a conversion to no gain, no loss, and unitary efficiency, 100% efficiency, not 200%, not 50%. In fact, you want a very low amount of noise. So all this conversion process that could have noise. And then there's also you need reasonable bandwidth. Those are real requirements. Practically, how you achieve it? Well, you need to come back to this nonlinear optics. So here I show you like a nonlinear media that sets the light to the nonlinear media. Well, you have the harmonic part, which is the dielectric constant, and then you have the quadratic coupling. Here, basically, the 3-way mixing, and you have a 4 mixing. So these the chi2 nonlinear T, this is chi3 nonlinear. And most of us, just simplify this picture right in a Hamiltonian, interaction Hamiltonian. So there's the chi2 coupling, and you got this 3-way mixing. And what is very important, I write this in expression annihilation operators. And there's a G0, which is called single photon coupling rate. Some people put 0 photon coupling rate, it's the same thing. And what it is, if you look at this G0, so basically you have a 0 point fluctuation in your 3 coupling mode and look at how many, what is the energy. So that in the G0 unit of hertz that measure the coupling between photons. 3 matrix configuration. For frequency conversion, we actually have one of the modes, and for this 3-way coupling, right? One mode is put in a stiff pump, it's a coherent tone. So we reduce that operator to just a photon number, square root of photon number, and reduce the 3 mixing to the 2-way mixing conjugate. So now you can see B convert to C, C convert to B. That's become a version. Carrier conversion. So what is the requirement to have an efficient conversion? So you want this number, square root of photon times G0 to be faster your loss rate. So the quantifier is so-called convertivity. So this number squared divided to the loss rate of this coupled mode. So you want your information exchange to be faster than the loss rate. So this is called convertivity. For coherent conversion, we want this convertivity to be 1. So if you see this is conversion efficiency, if your convertivity equals 1, it's a 4, 2 squared is 4, you have 100% conversion efficiency. And there are some pre-factor related to the loading condition of the cavity and the photon escape rate. The basic requirement is that you need the mode volume to be small. Okay, you need the quantity factor to be high to reduce the loss. And also, you know, basically that translates high Q non-energy, high Q, small mode volume, and the phase matching. And so those basically all the frequency conversion working this way, and this mode, the coupled ABC mode, could be optical mode, could be microwave photon mode, could be photon mode, could be Magellan mode. So if you think of it that way, and your nonlinearity actually can be very generalized. If you now, your nonlinear media right now have an optical photon, with a microwave photon, you have a string, you should write all the interaction terms here, okay? And if you look at each of these terms, this is a Chi2 nonlinearity that describes the quadratic coupling of nonlinear Chi2 material. Also describe electro-optical modulation, which basically this wireless field becomes microwave field, electric field. And you can also think that if you have a talking microwave, you have a magnetic coupling, that's magnetic Chi2 nonlinearity, magnetic Chi3 nonlinearity. So if you work on Josephson junction, and this term that dominant. Okay. And if you think about the microwave coupled to the optical wave in the magnetic material, and you have this Faraday effect, which is also like kind of a Chi2 nonlinearity. If you have a string, you have these optomechanics or electrostriction, which is the same thing, and I have a magnetostriction. Now you can think that there are all the different systems you can study with the nonlinear material. The coupling between photon, nylon, and that's all summarized here. But you see that G0, all those numbers are different. See, look at this. The Parker nonlinearity, Chi2 nonlinearity, a much bigger G0. But those Faraday effect, the magnetostriction is very weak. And the electrostructure actually becomes strong. So the mechanical deflection, mechanical strain actually very effect of the nonlinear optical material. And that's a very interesting insight. And that's also back to aluminum nitride. We have a piezoelectricity. We have a Chi2 nonlinearity. The action all described by this called a Chi2 tensor, right? So if you want an optical to optical frequency conversion, you work on the optical Chi2 tensor. You want a microwave to optical conversion, you work on this electro-optical tensor, which is coming from the same source. You can the symmetry is the same. You can also convert to photons. So aluminum nitride really all the different domains together, different excitation together. Okay, so show you just an example of a optical to optical frequency conversion. This device does the job. So you run this parametric oscillator in a non-degenerate pump here. You can convert this 780 to 1550. So basically, you can link a rubidium atom to a silicon light, and you can convert back and forth. And we can get a convertivity up to 4 when measuring the beam splitting, the mode splitting, and you can see that at the convertivity equals 1 here, which is about 20 milliwatts power, you get a maximum conversion. When you go even higher pump power, you convert back and actually sacrifice the efficiency. So this optical to optical conversion right now is a very general, widely practiced to convert different qubits on an optical frequency. Okay, and that phase matching is really critical to allow those different modes to come together. And what's really challenging of community has been this so-called microwave job. It is hard because a microwave has wavelengths like 5 centimeters. Okay, the optics are micrometers, so they are like a 4 order, 5 order difference. And then their energy also 4 or 5 order difference. That's quite hard. And the phase matching is really, really hard. And so here is our device, the realness microwave to optic conversion. And we designed the device, look like it's a strange shape because it's really a phase matching condition. What do you see over here? It's the optical resonator. Here there's a microwave one. And the microwave resonator made out of niobium titanium nitride and optical resonator made of aluminum nitride. They're separated by a very thin layer of glass, about a micron thick glass. It can couple together. And the phase matching actually very generalized. So you need the mode matching, you need energy matching, you need the optical momentum matching, all come together in this device. So what is the mode matching? The mode matching means that right now, if you look at the electro-optical tensor, there's most of those are zero. You want to leverage over the non-zero element. So if you look at the non-zero element, there's 1, 3, and 3. 3, 3 is very hard because you have all the optical field, the microwave field, also aligned to the c-axis. We normally want a microwave field to be in plane. That basically forces us to choose S13 index. And that means the component mode should be 13 and in 3 dot 113. So T, yeah. So you my microwave T mode and then the 2 optical mode has to be T and TM mode. The T one of the mode to be pumped, have the T mode, then and converted with a microwave T mode to optical TM mode. So that's mode matching. You also consider energy matching. I mean, there's a 2 optical modes, but it should be around 10 gigahertz. And match my microwave resonator frequency. Also, your momentum will be matched. So we know that microwave does not have a much momentum. The way we do it is that if you just want these 2 optical modes to have the same momentum, same as motor number, you have a problem. The problem is that these 2 modes have too much spring because so what we have to do is the intention is to have these 2 optical modes have a momentum mismatch by 1. In this way, they are not a perfect match. So their mode split in just around 10 gigahertz, 8.3 gigahertz. So the maximum microwave frequency. And what I need to do is compensate that optical momentum mismatch and to create that artificial momentum in microwave resonator. And that's why I have this above this inversion symmetry that give me pi phase shift when the microwave go around trip and give you momentum -1. And that's actually how we make this device to work. And there are a lot of detail over here. I'm going to skip that. And the final package device looks like this. Got a microwave connector, you got a fiber going in there. So microwave coming in and you actually get out the optical photons through optical. You can do an asymmetric measurement. This now your asymmetric measure is a 2-port, like 1 microwave port and 1 optical port. You can do that asymmetric matrix measurement and see this conversion efficiency. In this specific device, my conversion efficiency internally about 26% because I have a coupling loss. The waveguide conversion efficiency about 2%. So this 2% may sound small for you, but for us, it's like a 5 order improvement compared to previous R. So this is for us. And we actually try to make it much better. And the way we make it much better is to use a single crystal material. And we use this flip chip bonding device. And right now you can see that a little bit different. You have a 2 ring coupled together. There's microwave resonator. We can tune the microwave resonator by threading flags into the microwave resonator. And we can achieve the same goal, but use all sapphire of substrate. We have less heating or dilution refrigeration temperature. And we have a much better control of the thermal process with these devices. And that's something we are working on right now. And so a lot of important figure mirror is always about the noise, right? We want to convert coherent state to quantum state. We don't want thermal radiation into our mode. So a lot of effort in our group really need to measure how many noise photons in the device. Right now, it's a noise microwave photon, okay? So we build a very precise radiometer at millikelvin, and we can really measure how many noise photons present inside this resonator. For most of the pump power, our noise photon below 1. We can measure about 0.1 noise photon precision, microwave photon. Those are very hard. So when the power becomes too large, you start seeing noise in the system. Now you switch the pulse drive and you can reduce the thermal noise. The whole system actually get quite involved. If you go into my lab, you see all the electronics and optics they are put together, and those are done in the dilution refrigerators. And now we have quite a few of those, very complex, and the fiber actually go into 10 millikelvin stage, and really to convert a microwave photon to optical photon. Then go to fiber level. Here, this part we have not done yet. We need to still further connected superconducting qubits, and these are broken in at this point. We are currently funded by Department of Energy through this C2QA program as one of the half in the East Coast Design Center for Online Vintage. And our goal is actually to have two of these refrigerators talk to each other through the optical fiber, and that's a work in progress. And as you can imagine, need a lot of manpower, a lot of resources to work. And here, at this point, I'd like to give a summary, and I hope you will tell your story of how we can leverage integrated photonic chip by adding superconductor tied to material to achieve functions that manipulate single photon or achieve color conversion. Well, that's the end of my talk. And if you have any question, let me know. And this last acknowledgement, the work is really a summary of a generation of a graduate student and postdoc work extremely hard. And also the funding provided by the particular the laboratory for physical science, PRO, and Barbara and the community. Oh, thank you very much.
Very inspiring talk. And do we have any questions?
That's part. Yeah, interesting materials. Okay, come in. Here. And telecom wavelength is about a million. And the telecom wavelength is about 1 million. 1 million. Yeah. It's about 5 million right now. How do you grow? Those are like MOCVD. As you can see, the largest material to the sapphire, natural sapphire.
I was also very interested in the non-reciprocity that is from the beginning of this strong coupling. So, having a linear material, I don't make sense of non-reciprocity, but usually when the structure is asymmetric, in your case, it seems that they are doing it with the modes.
The structure is symmetric, the pump is not symmetric.
Can you explain a little more how you do that?
Yeah, it just depends on your phase matching, right? So there is always a pump in presence that does the job. People don't shoot if you don't see the pump, you don't see the yeah. Yeah, so basically you remember this was there was a pump there. The pump direction, which way put the pump in, the pump will be like clockwise or pump. Did I answer the question?
Yeah, I understand.
Yeah.
Yeah, can you show the Hamiltonian for the optical and electrorestrictive and these others?
Sure.
So,
Yeah.
so the electrorestrictive is the same. Yeah, it's same as the optical, right? So the electrorestrictive effect is actually optical effect.
It is.
If you think of the electric field as the
Right, but remember, that what's very interesting here is that when you talk about the G0, it's a mode, right? You have to look at mode. And the electricity is a Photon mode. Photon has very short wavelength. And that's why it's that G0 is much bigger. Even though you have a kind of nonlinear material, have a material nonlinear. And this nonlinear is a very general nonlinear. But your photon is much smaller. That's where you boost up this thing. Of course, I assume that you have unlimited power dissipation capability, which is not always the case. You use a photon, you also need to make sure the heat go away. So that's the major challenge.
A follow-up question. So, like, how does this direct microwave to optical photon conversion compare with if you basically convert your microwave directly to like acoustic photons in this piezoelectric?
Yes, that's the approach we also do. Yeah.
So how does that compare to the direct
They're comparable.
parallel?
Right. The hard part is that's how we do for almost 10 years before we do the direct optic.
I see.
Still a lot of community, a lot of people still trying that. It's really benefited from this effect. It's a very P0. And the challenge is that that's the double conversion from a microphoton to photon to optical photon. The first effect is very strong. In the end, the effect is the same, but you have more degree of freedom to work with. The intermediate photon mode, you need to control have no loss. Yeah, and I mean the photon mode, the Q is unfortunately not always a favorite. Yeah.
So I'm interested in the waiver version of microwave to optical. Right now, what's the current rate?
Oh yeah. So right now we are mostly interested in the superconducting qubits frequency, which is from like 3 gigahertz to 10 gigahertz to 11 gigahertz. And there was a recent work of Stanford and Chicago. They did like a 110 gigahertz. Yeah, it was very expensive set up, also power hungry. And there's really, for practical reasons, we are working on the 10 gigahertz rather than 110 gigahertz.
Like we're going to, so what determines the optical frequency?
We want to telecom wavelengths. We want to go into fiber. Yeah, of course, there are people working on the directly on the UV light. That does not propagate very far. Yeah.
Okay.
Okay.
Any other questions? All right. So let's yeah. So I have a question on the G2. Why it's limited to the G15? I thought like you have 100 detectors.
Data processing, that's already a lot of data. My whole hard drive cannot take that many data.
So that's the only limit.
Yeah, that's the only thing. It's a very long, lot of data processing. All right, thank you. I'll see you. Bye.
Very nice talk. I
What's your
really
name
enjoyed it. Yeah.
What's your name again?
Venkat Gopalan. Yeah. So, I'll send you some papers. We are actually working on a like that.
Right.
We have a paper we just got accepted in Optical Materials Express. But
Is that the paper that was